because we need to, there we got a couple people missing. All right, friction. How are objects in motion influenced by frictional forces? Do you remember what I said a while back about frictional forces? Frictional forces are caused by microscopic imperfections in the object, okay? Frictional forces, if you think about it, I want you to think, I've got a few things up here. We've got different blocks. We've got different surfaces. If we look at these guys right here on the desk, I've got some sandpaper, I've got a mirror. All right, if I'm supposed to slide something across the desk, will the mirror side or the sandpaper side be easier to slide? Mirror side, it's smoother, isn't it? Smooth to smooth. Okay, so now we've got this guy. We've got a wood side and felt side. Which one's going to be easier to slide? Smoother to smoother, right? Now, we're going to put this on the sandpaper. If I hook up a scale that reads newtons, you can see that. If I put this down and go to pull this, you can see that we are actually pulling some on this. This one's too big. Hang on. This one's a little easier to see. A little more sensitive. If we pull this guy, you'll be able to see that as I pull it, it's reading, isn't it? Now, one thing I want you to see is when I go to start pulling it, do you notice when I go to start pulling it, once it starts moving, that the scale, come closer and actually look at this. Once the scale starts moving, it's going to take a certain amount of force to get it going, and then you're going to see the scale drop. You ever notice it takes more to get something going than it does to keep it going, doesn't it? That is static friction, is keeping it still, and then eventually when we start moving it, notice how the scale drops and it's not as hard to move it, is it, anymore? Now, which side's going to be harder to move? You saw where the reading was for this one, right? Now watch the felt against this guy. Yeah, it don't move at all, does it? That's like Velcro, isn't it? That's how Velcro works. Those microscopic differences, you're actually getting to see more of an oscopic state where you've got imperfections here. It's rough. This is rough. They catch. That's what's happening. That's what's causing friction. Okay? Now, here's a question for you. Does friction depend on surface area? With all these microscopic imperfections, does it depend on surface area? How much area is in contact?
Yeah.
Take a look and see. Here we go. We're going to pull this. Right there, right? We're about a little below 0.5. Now let's turn it on its side. It doesn't really. You're seeing it a little bit, but it doesn't really depend on that. Microscopic imperfections are going to pull the same if we're pulling on surface area or on this area. It just means there's more of them in contact with this. Believe it or not, it actually read harder to pull on this side, didn't it? So you would think if you think it was a product of the surface area, the one with more surface area would be harder to pull, wouldn't it? It's not though. It does not depend on surface area. You know what it does depend on? Watch this again. What did I do? So the surface area contact doesn't matter, but the mass does. Because friction is a product of the normal force. Think about that. If you've got microscopic imperfections catching on each other, if you put more mass down, what happens? They catch harder and more of them catch, don't they? So how heavy something is does make a difference in how it pulls. How much surface doesn't, because the imperfections on this catch the imperfections on this, or if you turn it on its side, you still got the same imperfections here catching on the same imperfections here. So surface area doesn't matter, but mass, how heavy it does, how hard they contact, does matter. Does that make sense to everybody? Because that's often a fallacy that physics kids think. If the more surface area, the more friction. No, same friction. See? let's talk about this. Friction opposes sliding forces. It does. So friction is always opposite the direction of the motion. You might want to write that down. Friction is always opposite the direction of motion. Notice that. If we are pushing the block this way, which way does it show friction going? Has to be opposite if we're opposing it, doesn't it? Okay. It's caused by microscopic irregularities. What are some of the disadvantages of friction? Yeah. It makes something harder to push or pull. It also wears stuff out. Think about friction. Where do you see friction? In your engine, right? Think about it. You've got a piston and a cylinder. You've got a cylinder here, and the piston goes up and down in the cylinder, which causes it. Do you even know how an engine works? The cylinder and engine works? Combustion in the bottom pushes the cylinder up. There's a rod connected to it which moves pieces in your car, which then moves your axle, which then moves your transmission drive shaft, which then moves your tires, because you have a differential that switches that motion from this way to that way, and rotates your tires. Well, this is metal and this is metal. That's a whole lot of pushing against each other with microscopic irregularities. So what do we have to put in our car engine to keep that from getting really hot, swelling up, and seizing? Oil. That's why it's really important you have oil in your engine. If your oil gets low, then this is going to swell up, which means area is going to get smaller. This is going to swell up, get hot, and swell out. And what's going to happen is eventually they're going to swell and your engine no longer move. You throw a rod, something like that happens, right? And you're going to have a new engine. So it's important. Friction is a bad thing sometimes. Do the soles of your shoes wear out eventually? That's friction. That's frictional wear. As you walk across the floor, friction is why we can walk. That's under the positives. If we didn't have friction, you could not walk across the surface of the earth. Think about it. Think about an ice rink versus this floor. Would you want the entire world to be an ice rink? It'd be hard to walk, wouldn't it? Think about it. I used to do the time clock when I had hockey players, when we had hockey in town. I actually took my tennis shoes and put these little things with spikes on them. I made my own friction. I could walk normally across the ice because I had little pitons on the bottom of my shoes. It caused little points it dug in, right? It was little frictional points, basically. I made my own little irregularities as I walked, so I didn't go, woo, and slide out, and go, ha, and die, because nobody wanted that, because then they'd had to find somebody else to run the clock. All right, so it wears things out. Now, control of motion, advantages allows for control of motion. Why do you think tread on tires is so important? That's friction. The contact between the rubber of the tires and the road is friction. It's why you need grooves to get the water off, because you need to be able to touch the asphalt, don't you? Walking is the biggest, though. Rolling, you can't roll without friction. Factors that affect the force of friction. Normal force. And what did we say? It is independent of what? Yes. It does not matter how much of the surface is in contact, just that the surface is in contact. It depends on how heavy something is. Static friction. Let's talk static friction now. Static friction, if you'll notice static, the word static means what? Still, right? Static means still, not moving. Okay, so this is the friction of an object that at rest that's trying to move. Okay, this is starting friction or resting friction. It's the thing that keeps something from moving until. This is the type of friction that is involved when you're playing tug of war. You're trying to have a higher static friction than the other, more mass, right, than the other guy's team does. And they're trying to break your static friction and make it kinetic friction and make you move. Okay, so this is starting friction. It is always higher than kinetic friction. Okay? The force of friction static is always less than or equal to mu sub s, which is the coefficient of friction, times the normal force. Notice this is not an equal sign. I want you to think about why it's not an equal sign. And kids had the hardest time understanding this, so maybe with my little demonstration I can tell you. Here we go. I apply a little bit of force. Is this thing moving? So static friction is still working, isn't it? I apply a little bit more force. This is really good. Let's do it. A little bit more force, a little bit more force, a little bit more force. So I don't have to get all the way up to equal to, because once I get, so it can be less than the static force of friction, can't it? Because it's still not going to move. Eventually I will hit the static force of friction and it will move. At which point you saw this thing drop down a little bit, didn't you? Kinetic force is constant. It does not require more force to get it to a certain point. I have static, 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 and then it drops down and it becomes a line. So it's going to build up until it hits where it'll move, and then it drops off and becomes level. Because then I only have to maintain a certain amount of force to keep it moving, which is less than what it took to get it to start. So do you understand why static friction is a less than or equal to, but kinetic friction is only going to be an equal to?
Potential energy.
We'll talk about that when we get to energy. Let's not jump ahead. But see what it says right here? Only as big as it needs to be to stop motion. That's what I'm talking about. Once the force of opposing friction passes the maximum value, the object starts to move and kinetic friction works. So this is the friction. Once an object is already moving. Okay? Unlike static friction, kinetic friction is always the same value. In other words, the force of friction kinetic is equal to mu sub k times the normal force, but it's equal. So this guy is less than or equal to, but this guy is just equal to. And if you want to know what the graph of that looks like, it's linear. The force of static friction is linear, 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 and then it drops down like this. So this is going to be my force of friction static, and this is going to be my force of friction kinetic. So does that less than or equal to make sense, and the equal to make sense in this picture on this graph? Okay.
So if it were equal, it would just bottom out at that top point.
Yeah. But it doesn't. It actually takes less. Once you think about game of tug of war. The biggest, the hardest part is getting the other team moving, isn't it? Once you can get them moving, It's not as hard to keep getting them moving, keep sliding them towards that line, is it? It's just breaking that coefficient of static friction. They're dug in and leaning back, and they've got feet on the floor, and that big heavy guy who's the anchor, right? You got to get him moving, really. And once you get him moving, then you're just pulling across the floor, aren't you? So it's less force once you break the seal, so to speak. And think about it from a microscopic standpoint. You're locked in, aren't you? But once you get enough force to lift it a little bit, now they're not quite as hard locked in, are they? They're still catching as they go by, but they're not catching as hard, are they? So does that make sense why it takes more to get it to kind of break across first, and now you're just keep on moving? Now if you stop it, then it goes back to you needing static friction again, don't you? Because it settles back down into all those little microscopic imperfections. I love friction. I think friction is actually really fascinating. It's a fascinating thing. All right, sliding friction versus rolling friction. Okay. Sliding friction acts against the direction of the sliding motion. And then rolling friction. In the direction of the motion. What? Wait a minute. Didn't you just say up at the top, Miss Duffy, that it always acts against the motion? It is still acting against the motion of the wheel itself that's turning. Think about it. The car is going forward. The wheel is moving what? Backwards, isn't it? So if the wheel itself is turning backwards, which direction is the friction? Forward. So do you see what that means? It is technically acting in the direction of the car is moving, or the object is rolling, but it is actually, in fact, acting opposite the direction of the actual rolling object itself. Okay? So what I said at first stands, but it's very important that you understand that. The wheel goes this way, so the friction goes that way, and the car is going that way. All right? So here we go. While the force of friction depends on the normal force, the coefficient of friction only depends on the type of surfaces in contact. By the way, what do we mean by that? We had at some point that mu is equal to the tangent of the angle of the incline that it causes it to break the surface. It's a higher angle for static friction, and then you can actually lower it. But that's because it doesn't depend on the normal force really. It just depends on the material, right? Those microscopic imperfections. Okay? Now, how can friction be increased between the tires of a car and an icy road?
Chain. You know the things they put on?
What are the things they do? Yeah. Roughness of the surface, that's why we put chains on. Salt, that's why salt's a different reason. Salt's a chemical reaction. Sand, right? Or what do people do? They put extra weight in the back of their pickup trucks, don't they? Think about it. Why do you do that? Because pickup truck bed is lighter in the back, and you don't want the back to be lighter than the front if you're on an icy road, because then it starts to move more than, you see what I'm saying? So they put heavier weights in the back so we can increase the mass, or we can increase the roughness of the surface. That's it. We use salt or beet juice, believe it or not, because it increases it lowers the melting temperature of the ice. So it actually causes it to melt faster. That's not actually friction. That's a chemical property, but we do throw sand If you've ever been out when it's icy and it's just really, really cold and they know it's not going to be able to melt it that way, they'll throw sand on the road to try to give you some more traction. Okay? All right. Here we go. Filing cabinet. A 24 kilogram filing cabinet is initially at rest on a rough surface. And by the way, before I forget, even if we don't finish, you do have a homework assignment. That's the piece you picked up last, which is the PET lab thing. It's not a lab, but we will put it in our lab notebooks. It's just a mini lab, okay? But your homework, before I forget, since it's 11:20 and we get out of here at what, 11:25? Yeah, in 5 minutes, we're going to do this problem and then you guys can move on. We'll finish these notes up next time, okay? We're always, never have enough time, do we? But we're learning good stuff, right? Okay, here we go. 25 kilogram cabinet is initially at rest on a rough surface. The coefficient of static friction between the cabinet and the ground is mu sub s. And the coefficient of kinetic friction is 0.3. By the way, static and kinetic friction are usually between 0 and 2. Kinetic friction is usually only between 0 and about 1 because from what I said, it's less than static, isn't it? The higher the number is, the more friction there is, the rougher the surface is. Make sense? Okay, here we go. We've got a filing cabinet. Moving on this filing cabinet, we want to know the cabinet is pushed by 100 newtons. Find the magnitude of the force of friction. So, free body diagram. But what forces are acting on this? Do what? Normal force, absolutely. What else? Gravity or weight? What else? Okay, which way friction? To the right or to the left? To the left. And what else? Force applied. So F sub A. Okay. So now, sum of forces in the x direction. Well, it doesn't even ask us that, does it? What does it ask us? For the force of friction, doesn't it? What did we say the formula for force of friction was? Mu times the normal force, doesn't it? Well, what is the normal force? Look at your graph. Look at your free body diagram. What is the normal force equal to? Yeah, this thing is only moving in the horizontal, isn't it? So if we do the sum of forces in the y direction, which is ma, that's 0, isn't it? So we know that the normal force is equal to the force of gravity, which is what? Mass times gravity, isn't it? That means the force of friction is equal to mu times mg in this case. Well, what is mg? 24 times 9.8. Okay. So if it's initially at rest, what's working on it? Which one are we going to use? Static or kinetic? Static. So static is what? 0.5 times the mass, which is, and then gravity, which is 10, right? We'll just use 10. Half of 240 is 120 newtons. The force of friction is 120 newtons. Okay? This would have to be mu sub s because we don't use mu sub k until it is moving. Okay. So here's my question. Did they get the cabinet moving? What was the applied force? 100. What is the frictional force? They did not get it to move, did they? That would be the next part of the question they would ask you in a test. Then it would start, you would be right at starting to move, yes. It wouldn't move until it's greater than, because remember, it's less than or equal to. So until you break over that 120, it will not move. So, all right, guys, do the Fat Lab. It's on it's on static versus kinetic friction. It gives you a chance to look at how changing things affects how stuff moves. Okay? Yeah. I'm just gonna. I recorded it. Yep.